Hello, fellow problem solvers. So today we're going to be doing a problem from the 2011 IMO, problem number 2. This is a famous windmill problem for which you need absolutely zero theory to solve the problem. Now, nonetheless, it is a very tricky problem, and I invite you to pause for a minimum of 2 hours, ideally 3 hours, but not more than 5 hours to try to solve this problem. If, on the other hand, you would like to go along with us, I suggest you take an initial 45 minutes and try to solve the problem. So now, let's begin. So, in the beginning, when you don't know what you should do with the problem, the best strategy is play around with the problem. Namely, here, what this means is, let's play with some, and say, for n equals 3, whichever 3 dots we have, if we put a windmill here, and the windmill will go to this dot, say these are dots A, B, C, we'll get the windmill will then transform here, go from A to B, and then it will go from B to, it will start rotating on B, and it will rotate like this, A, B, C, and then it will go to C, and so on. Then it starts rotating on C as the pivot, and then it goes back to A, and so on and so forth. Now, initially, when you're trying to solve this problem, I suggest you take 30 minutes literally playing around with all sorts of ABC. Say this is a case where it works, but say if we take 4 points, does it always work? No matter where we put the windmill? If we put it outside here, if we have a ABC, 4 points here, does the windmill always work? And in this case, if I put the windmill here, it will go from A to C, then it will go from C to B, and then from B, then it starts rotating, goes from B to D, and then from D to, it seems, from D to C, and then from C to A, and we're back again. From A to C, it seems, from C to A, and then it seems it's going to go from C to A, and then it goes to D, I think. Yeah, it goes to D, then it goes to B. It has a big thing. But this is another case that it seems works no matter how you put the windmill, if you put it like this. But say you have points A, B, C, D, such that the points A, B, and C make a triangle, and D is the point inside that triangle. Does the windmill still work? And the answer is it works sometimes, but not other times. And I would really invite you to pause for 30 minutes here and try to see in which cases does the line you set work, and what ideas can you see? Like, what are your first thoughts here? Like, what are you trying to do? I really invite you to play around and then come back in 30 minutes. And here's sort of the first set of ideas. Okay, so in this problem, what I also want to talk about is sort of the problem-solving philosophy. The idea that you will come up with many different ideas. Some will fail, some will succeed, but you should expect most of your ideas to fail. And the idea is you need to balance going into depth with your ideas, exploring your ideas deeply, with the flexibility to switch between different kinds of ideas. And always, while you're trying to solve problems and you're playing around with them, you're trying to see what it is you notice. You're trying to find rules, trying to find what needs to be true in the problem as you play around with it. Especially these types of problems where there is a transformation happening, where there is a action taking place. What is happening when the action is taking place? What do you notice? Do you notice anything you can formalize? Those are the questions you need to ask yourselves when you're trying to solve problems like this. Now here, the first idea that came to my mind was, okay, if I have a convex hull, which just means the outermost points, if you have a group of n points where here n is equal to 9, these 5 points are sort of the boundaries, so to speak, of this set of 9 points. Like everything is inside the lines formed by these 9 points. That's what a convex hull is. Anyway, my thing was, if the windmill, like if it goes through, so the first idea I had was if it goes through a point infinitely many times, it seems it should go through the same point on the same windmill position should happen on the same point infinitely many times was the sort of idea that when I was exploring the problem, was the thing I saw. And also here in the convex hull, I figured if the line's over here, like outside of the convex hull, then if it rotates, it will get to this point, and then it will rotate on this point, then gets to this other point, then it will rotate from here like this, and it will get to this point right here, then it will rotate. You can imagine this line rotating here, then it gets to this point until it rotates, gets to this point, then starts rotating towards this other point, and finally gets there, and then we get on these same things. So the first sort of thing I got was, maybe I can think of convex hulls within convex hulls. And maybe the most important thing is that the line is sort of initialized in the innermost point in the convex hull. Maybe whatever point I choose, whatever line I choose here will work, because it's in the innermost convex hull. Or if there's a point here, I just need to make sure that the initial windmill is on that point and it will be there forever. However, and this is where this flexibility comes in, which is very common to problem solving, I realized that this idea is going to become very complicated. I can't still figure out what I'm supposed to do with it. And after exploring it a bit more, I figured that maybe I need to go back to the drawing board. Maybe I need to go back and try to figure out if there's other things I can notice when these transformations are happening. And this is also a common heuristic for general problem solving, coming from Engel's book on Olympiad problem solving, which is when you have a transformation happening, look for an invariant or a monovariant. Now, what does that mean? It means, like, say here, we're having some transformations happening, like we have this line, and it's going from place to place. A transformation is happening. So it will go from here, and then it will go to, say, we'll go to this line, and then it will go to this other line, going here. Then we go to this line again, then these almost look collinear. But the idea is there's a transformation happening. And the question is, when this problem is transforming, what stays the same, or what changes in a controllable or a predictable fashion? So looking into, say, our 3 points in the beginning, say we had, say, 4 points, the case that failed, we have A, B, C, D. What is always staying the same as the windmill is moving? Is there something that isn't changing when the windmill goes from D and now goes to C, and now it starts rotating on C, is between D and B, and then is on B, and it's rotating between C and D? Is there anything that stays the same? And what is really the difference between this windmill that succeeds and this windmill placement which fails? Because if the windmill is going through all the points infinitely many times, it doesn't matter which point we begin on, because if we figure out the correct windmill, it shouldn't matter which point we begin on. That is sort of the idea. It's just used in the problem, so you don't have to worry about, oh, am I choosing the correct point? The idea is big picture. If I choose the correct windmill angle on a point, it doesn't matter which point I choose. So the idea is, like, how are we going to do this? It doesn't matter what point we're choosing. What matters is what windmill placement we put on that point. And now here I really invite you, if you haven't gotten any idea on a monovariant or an invariant, something that doesn't change or something that's changing controllably as the problem is changing, I really invite you to draw a picture of ABCD like this, and then play around with, look at the different states the whole problem is in. So you have this here, and then from here you will get to the place where B is in control, like this, C, D, and then you'll get into a place from here where C is the pivot, and then you'll get to a place where A is the pivot again. You'll get to this place. You'll get in a cycle, and you'll keep going in the same way. Now, is there something that remains the same in this cycle as opposed to this cycle? Like, what's changing and what's staying the same? Like, or alternatively, what are the things you notice here between these two different solutions? I invite you to take 10 to 15 minutes, like, play around, see, what do you notice? And here's what I find. So here's the big idea. Namely, after playing around, I labeled these points X and Y, these top ends. Because what I saw was that the windmill's here, then it goes here. So it's on D, and then it goes to C, then it goes to B, it's rotating then on D, then it rotates on A, then it switches and goes to C, then from C it goes to D, from D it goes to B, and then from B it goes to A, and then from A it goes back to D. But the thing that I noticed is that it always gets back to its original position at the original angle. So here, and it was here like this, and also it was like here like this, but these are two different sort of positions, if you want to call them, of the line, because this one's below this one. So the first thing you notice, in both in the solution case and in the non-solution case, is there is a periodicity, there is a cycle here. So here, look, the cycle is much easier to figure out on the non-solution phase, in the non-solution configuration, because we have, it goes here, then it goes here, goes to C, then goes to A, and it goes back on the same place. It is much easier to figure out that there's a periodicity, a cycle, that it cycles through the points in the same way every time. That when it does this infinite thing, it will do it the same way every single time. And now with this knowledge, I really invite you to take another 30 minutes and try to figure out, is there anything more you see from this labeling of the windmill, from looking at, okay, we have something that doesn't change, namely that is going to come back to the old place infinitely many times, is going to do a cycle, so to speak. Is there anything else you may notice, any way you may see that we could prove it goes to the same cycle, or anything else that could be useful? And the advice here is notice stupid things. In a lot of these problems, it's about noticing things that you really think when you read the solution, wow, that was so trivial, so easy, so stupid. How did I not see that? And the thing is, we often miss the stupid things because we're looking at something very complex. But you gotta start stupid, start easy, start simple, and then move on to complexity. Because complexity, at the end of the day, is built up from a couple of simple, easy ideas. And here, I invite you to look at this, to draw your own picture, look at the changes and see what is happening here and what is happening here. Is there something that isn't changing? Like, is there something that isn't changing that we might use to solve this problem, to figure out the best way to pick a good starting line for any point? What do you see? That's really my question here. And I invite you really to take another half an hour, even to an hour, and try to figure out the next thing that you see. What's happening here? And here's what's happening. And here's the idea. Namely, what is the difference between this line, which doesn't solve the problem, and the other line, which does solve the problem in this case? Well, if you look at maybe the line xy, and look at it from x to y, let x be down, y be up. The thing that's on the right side of xy, there's 0 points on the right of xy, going from x to y. Here again, there's 0 points on this side of xy. Now we go here. Again, if we look at the right side, so this is up from x to y to the right, there's 0 points. And here again, to the right of xy, from x to y, remember we go from x to y, and then on the right, there's 0 points. And then back again, there's 0 points on the right side of xy. And now look at here, on the right side of xy, if we go from x to y, then this is the right side, we will find 2 points, A and C. And then when a switch happens again, we will find how many points? We'll find xy, A and D, 2 points again. And again, we go to B, there's again xy to the right, there's 2 points, AD. Again, xy, 2 points, 2 points, 2 points, always 2 points on the right side of xy. And it rotates back to the original place where it had 2 points to its right side. Now with this idea, I invite you to pause. If you haven't figured this idea out, I invite you to pause and see, is there any use to this idea? Or is it like our convex hull, maybe too complex at the moment, and we need to take another 30 minutes and figure out another idea? I will let you be the judge of that, but take half an hour and see if this is useful. Evaluate it yourself. Here's my next step. So the first order of business is really seeing, is this invariant even good or not? And let's see, so if we have a general case, xy, a point P that's on the pivot, and it's going to go to this point Q. We have k points on the left side of xy, and n minus 1 minus k. So let's see what will happen. It'll go to the point Q, and then Q will become the next pivot. And what happens is, point P will go on this side of the line xy. As Q is on the right, P will go to the right side of the line xy, and we will still have n minus 1 minus k on the right side and k points on the left side of the pivot. So it seems that this thing actually is an invariant we can use. It doesn't change as the process keeps giving us different points as the pivot. Now let's ask ourselves, how can we use this in the general case? Well, there's a couple of things. One is, okay, this always stays the same, but another question is, when the line xy, so say P, it has a line which has k points on one side and n minus 1 minus k points on the other side. And then there's some other point, say T, which also has some line, which has, if we orient it a certain way, say xy, this line also has k points on one of the sides, on the left side, and n minus 1 minus k points on the other side. Do we know that this thing, this windmill, will come to T at some point? Is there any use for this? Like, that's the next sort of question I ask myself when I see this. Will this be of any use? Like, how do I know it's not going to come to some other point and not T? As it goes through some points in the line, will it come to this point T or not? I invite you to take 20 to 30 minutes to try to figure that out. Will it or will it not? And the answer is, well, let's say, okay, there's a line xy. How could it miss it? So let's see, this line will make a full circle. It has to. Simply, we can look at its rotation in general. Like, we can make a line on the plane that sticks, and we can look at the angle xy makes with that line. So it will always be, it will be making a smaller angle here, like yx will be intersecting it, and then xy will be intersecting this fixed line, and we'll be making a smaller than bigger angle. So we can generally see this xy will make a full turn, and it will come at an angle like this, that it goes through T. Now what happens if it's not on T, if it's on some other point at this angle? Say call the point S. And when it's on S, xy, then it has, you would say, so how many? So it's on the left, there's k points. K points on the left and n minus 1 minus k points on the right. Can this be the case? And the answer is no, because if S is to the, say we draw these parallel lines and S is to the left of T, then just like moving this parallel line, we are adding points to the right side of xy. When we're moving the line xy, when we move it here, we added a point to the right side. Now it has n minus k points as soon as we move from T. And it keeps increasing. The number of points to the right side of this line xy keeps increasing. So in that way, there can only be really one line such that xy goes through that point, and it has n minus 1 minus k on one side and k on the other side. Specifically on the right side, it has n minus 1 minus k, and on the left side, it has k points. So now that we have sort of this, so this means that if there is a line, if we have a point P, and we run the windmill such that the windmill xy has k points on the left side and n minus 1 minus k points on the right side. That means they will have to come to every point which has a line that once you draw it through that point, it has k points on one side and n minus 1 minus k points on the other side. So now with that sort of intuitive proof, I invite you to take 20 minutes to an hour and try to finish the problem. Here's how it's done. Okay, we have a point P, and let's take a second and look at why this case failed with this line on A. Well, it failed because, say, if this is xy, then this is a line through A, which has 0 points on the left side. But the problem is, there is no line through D, which has 0 points on its left side. No matter how you define the line or left, there's just no line like that. There's always at least 1 point. I mean, there is always 1 point on the right or left, depending on what you define right or left, when you draw a line through D. So now this means that we need to find a k such that no matter what the point, we have a line through that point P, which has k points on one side and n minus 1 minus k points on the other side. And the question is, how do we find that? Well, the first idea is, and you can get this while playing with other bigger values of n, is that, number one, if we have a line with k points on one side and n minus 1 minus k points on the other side, we have a line with k plus 1 points on one side and n minus 2 minus k points on the other side. Why? Well, we just windmill the line, gets to a point. What's the first point we reach? I think, let's say there's a point here. We reach this point first. So if we draw a line like this, we will get, now we will get k minus 1 points on this side. But we can also get, then we need to draw a windmill in the opposite direction. Say we will get to, say, a point here first. So if we draw the windmill here, then we will get k plus 1 points no, wait a second. If we're getting k minus 1. Oh, but here's the thing. We can, as we're rotating this line, we will get to a place where x and y change sides. And then we will have k points on one side, on the right side of xy, and n minus 1 minus k points on the other side. Now, what does that mean? Because we have been rotating this line, and every time we rotate and put a point on one side or the other, it increases or decreases the number of points on the right side by 1. So it means we got from k points and n minus 1 minus k points. On the right side, we had k points, and on the left side, we had n minus 1 minus k points. Then we got to a place, after a bunch of switches, with n minus 1 minus k points on one side and k points on the other side. Now, what does this mean? This means that we also, because this number, always increased or decreased by 1. This means we got all the numbers from k till n minus 1 minus k. And I would invite you, to take another maybe 5 to 15 minutes and see why this is true. If I am here and I have k points, I have n minus 1 minus k points here. Once I do a half circle and I get to the other side, I still have n minus 1 minus k here and k here, but the right side and left side have changed. What is right and what is left has changed. That I must have gone through all the numbers from k to n minus 1 minus k. And I'm assuming here that k is less than n minus 1 minus k. It's a thing of notation, really. So now what that means is that I can get any point between k and n minus 1 and minus k. So it means I can get any line from k points on the left side and then minus 1 minus k points on the right side. I can get any number of points between k and n minus 1 minus k points on the side that I want for any single point. And now with that in mind, it makes sense to look at k equals n minus 1 over 2. And if n is even, then let's just take the floor of this, or the ceiling. It doesn't matter because the floor will have floor on the one side and ceiling on the other side. And now all we need to prove really is that we can get this many points for each point. And to prove that is something that I'll actually allow you to take 5 to 15 minutes and try to prove that we can really get that. It's almost obvious, but I still want to allow you the time to prove that. We can always get that. I mean, it's actually what it really comes down to. It's not really thinking. You take 5 minutes, I'll just show it now. Here it is. If we had s and then minus 1 minus s, assume s is less than n minus 1 minus s, less than or equal to. So This means s is less than or equal to n minus 1 over 2. And this means that n minus 1 minus s is then going to be greater than or equal to n minus 1 over 2. So we can always get a number between. So we can get any number here, and n minus 1 over 2 is in this range. You can do odds and evens case, it doesn't really matter. And with that, you can always find k equal n minus 1 over 2. Floor of that, points on the right side, and the ceiling of that on the other side. The ceiling? I think, yeah, the ceiling on the other side, if my algebra is not mistaken. And with that, you can go ahead and write up the problem solution. And that's what we'll do just next. I invite you to take 20 to 40 minutes and see if you can get all these ideas together and write the problem solution. We'll do that now. So first comes the invariant, namely, we define an orientation of the y with points x, y, and we define the right side and the left side of that line. And now notice that when the pivot changes from point P to point Q, the point P will be on the same side that Q was before the change of pivots took place. So this means that the number of points on the right side and on the left side of this line, the windmill, remains the same throughout this process. And now we move on to the second part of the solution, namely, there exists a line through P, element of S, whatever P may be, with the size of S minus 1 over 2 points on the right side of that line. And now how do we prove this? Well, we say that take any line which goes through P and has k points on one side and n minus 1 minus k points on the other side. Then we know when we rotate this line 180, it will have n minus k minus 1 points on the right side and k points on the left side. So because it went from k to n minus 1 minus k points, where the size of S is equal to n, what we have is that we will get, because the number of points on the right side of the line changes by 1 when we pass any single point, that means we'll be having every number of points. We'll have a line through P which has S points on the right side of that line if S is an element of k and n minus 1 minus k, assuming that k is less than or equal to n minus 1 minus k. And now with that, if we assume k is less than or equal to n minus 1 minus k, which we can without any loss of generality, that means k is less than or equal to n minus 1 over 2. And because k is an integer, this means that k is less than or equal to n minus 1 over 2, the floor of that. And given that this implies that n minus 1 minus k is greater than or equal to the floor of n minus 1 over 2, that means that we will be able to get k equals n minus 1 over 2 points on the right side of P for any point P. And now with that, we finally move on to the third point, which is the fact that if the windmill had k points on the right side as it was on P, it will go to the point Q, which has a line through it with k points on its right side. And the way we show this is we say draw P, it had k points, and then there's Q, it had k points on the right side, and say that the line through Q, which has k points on one of the sides, is this. That's the line L. Assume the windmill never came to L with this orientation, and take the same line L prime, where the windmill actually was when it was parallel to the line through point Q, which divides it into k points on one side, and then minus 1 minus k points on the other side, then we will have that a contradiction. If this windmill was on point Q prime, we will have that if Q prime was to the left of Q of the line xy, the line L, which divides Q into k points on the right side, then line Q prime will have more than k points on the right side, which is a contradiction. If it's on the right side of q, it will have less points on the right side than q, which is again a contradiction. So this means that the windmill passes through point q. And with these three facts together, we know if we choose the windmill such that it has n-1 over 2, the floor of that points on its right side, then it will go through every single point once. And because it does a rotation every time, and it does this rotation infinitely many times, it will go through all the points infinitely many times. And as always, thanks for problem solving.